Okay, relative to some of the conversation that was going on in the chat, I've written the law of conservation of energy here. We'll come back to that. Right now we're concerned about potential energy. Okay, so we see that this function, whose derivative is this function, and this function then being an antiderivative of this function, for reasons that should be clear if you understand everything we've done so far. We find that this is the graph of the negative of the change in potential energy from 1 centimeter to x. Now we want to do a graph of potential energy relative to x equals 1 centimeter. Had to find a piece of chalk. Okay, the potential energy relative to x equals 1 centimeter is equal and opposite to this curve. Now let's just analyze that a little more closely. Okay, this dotted curve is meant to represent this curve that we get from this integral, whether we do it numerically, as we might have to do if we don't have a good function, a good symbolic function, and or analytically, if we have a symbolic function we can integrate, we can actually get this function. Okay. Anyhow, that's the function we have here, and that's the negative of the potential energy change from 1 centimeter to x. Now let's take a typical x. Then this negative change in potential energy from 1 centimeter to x, and I didn't put all the subscripts 1 centimeter to x in here, but here's your negative of your change in potential energy. So here is the change in potential energy from 1 centimeter to x, just being equal and opposite to the negative of this quantity. So if our potential energy change from 1 centimeter to x is this much, and here's x equals 1 centimeter, where the potential energy we take to be 0, and let's back up a little bit. Potential energy relative to x equals 1 centimeter is the potential energy function that we get if the potential energy is 0 at x equals 1 centimeter. So if the potential energy is equal to 0 here, and if the change in potential energy from 1 centimeter to x is this, then that means that this point is a point on the graph of the corresponding potential energy function. Now remember, where we put the 0 of potential energy is always completely arbitrary. Once we've done it, we're stuck with whatever potential energy function we get from that assumption, but potential energy can be measured from any point. So here we're measuring it from the 1 centimeter point, and you see that what's going to happen is this point is going to be here, just upside down from where this point was in the curve, and if you do that for any point on the curve, you're going to get the same thing. The potential energy function there is going to be the reflection of this function through the x-axis. So here's our function. Actually, this function can be represented as the change in potential energy from 1 centimeter to x, and that equals the potential energy relative to x equals 1 centimeter. So if we want a potential energy function relative to x equals 1 centimeter, this is it. Now what would we get if we wanted to find the potential energy relative to x equals 3 centimeters? Well, that would mean that our 0 for potential energy is at 3 centimeters. The change in potential energy between any 2 points would be, well, I'm going to stop for a second because I want to put a couple of things on the board, and when I come back we'll see those couple of things. I paused there because of my labeling up here. I'm not able to draw what I want to, so I thought about that for a couple of minutes and decided wasn't really feasible to do that. Okay, here's a curve, change in potential energy from 1 centimeter to X. Here's the 3 centimeter position. Here's the point on the graph for the 3 centimeter position. What's the change in potential energy from the 3 centimeter position to the 2 centimeter position? Well, we can see that that change hopefully you can read that. Delta PE from 3 centimeters to 2 centimeters would be represented by this arrow here. So from the 3 centimeter position to the 2 centimeter position, we have a change in potential energy that goes like this, which gives us this point on this graph. From the 3 centimeter to the 1 centimeter position, the change would be represented by this vertical displacement, so that the point will be here. Okay. In other words, if the 3 centimeter position is our 0 for potential energy, then here is our 2 centimeter potential energy, here's our 1 centimeter potential energy, and then our other potential energies from 3 to 4 centimeters is going to go down a little bit, from 4 to 5 it's going to go down a little bit. So we're going to have something like this. We're going to get these points, and what's going to happen is this curve is just going to repeat itself. It's just going to be raised up higher. Okay, now remember that the 0 point for your potential energy, the point with respect to which you measure your potential energy, is completely arbitrary. We could pick any point, make it the 0 of potential energy, and then we just basically lift or lower this curve accordingly. If we wanted the 5 centimeter position to be the 0, we'd find the 5 centimeter position here. We'd grab the curve here and we bring it down to 5 centimeters, and you would have that curve. So again, the position is arbitrary. Ultimately, the easiest way to do the potential energy for this situation, where you have a force that's always that's always positive, as would be the magnetic force, it would get very close to 0 very quickly, would be to do the potential energy relative to infinity. Now, the potential energy curve does have an asymptote. Okay, you can think about why that would be, but if the force curve approaches 0 as an asymptote, the potential energy curve has to have a horizontal asymptote. And actually, that's not even true. You do a p-test, so kind of ignore that statement. In this case, it's clearly true. If the force falls off at a rate greater than a 1 over x graph would fall off, then you're going to have a horizontal asymptote for your potential energy. So you just raise the graph up to where that horizontal asymptote becomes the x-axis. So this would be a graph for the PE relative to infinity. This is going to be very important. This whole idea of a potential energy relative to infinity is going to be very important later in the course sequence when we talk about gravitation a little bit later in this course, and then again when we talk about electromagnetic or electrostatic forces and even magnetic forces in second semester. Okay, so we again simply establish that this curve has a horizontal asymptote. We raise that asymptote up so that it's along the x-axis, and that's our potential energy relative to infinity. And we would interpret that as being, okay, if we move from, let's say, this point to infinity, our change in potential energy is going to be negative, and it's going to be equal simply to this vector, because if our potential energy doesn't hit zero till we get to infinity, then our change in potential energy from here to infinity is going to be this. Okay? The potential energy at this point to the potential energy at infinity. The potential energy at infinity minus the potential energy at this point is represented by this vector. And you might want to think about why that's the case. So I could label this arrow delta PE from x to infinity, where this point is x. Again, this potential energy curve is what it is. It can be raised or lowered, and when you raise or lower it, wherever you intercept the x-axis, that's the 0 point for measuring potential energy.